Hi guys, sound check.
Hello.
Okay, hi guys. Are you ready for some cool stuff for today?
Yeah.
Okay. I'm going to cover several topics today, and one of them, and the most important one, is the cryptography. So we're going to learn how to encrypt and decrypt messages and send and broadcast them. So, but I want to start with several technique claims we will need later on. So the first one, the last time we discussed the Chinese remainder theorem, and now I want to present a different form of the Chinese remainder theorem. It will be slightly different statement, but it's very useful one. So, claim. So suppose we have two positive integers, m and n, which are coprime. So m and n are positive integers. And we have this map. So first of all, we have zmn star, zm star times zn star. So what are these? So this is the set of all integers from 0 to m minus 1, which are coprime with m. And this is the same for n. This is the direct, this set is a group with respect to multiplication. And this is a direct product of groups. And here is another group. And we have a map, which goes from left to right by the rule. K goes to K modular M, K modular N. Exactly the same rule as we have in the original Chinese remainder theorem. And I'm saying that this map is a well-defined isomorphism of groups. So let me see. The name of the map is psi. So the claim is that psi is a well-defined isomorphism of groups. Just in case, well-defined means that it actually takes all elements from here. So this is the claim. If you have any questions regarding the claim, please ask. And if there are no questions, I will proceed with the proof. So let me recall the original remainder, Chinese remainder theorem. So it says that exactly the same map, but on a different target with a different source, which is this, is a bijection and preserves, so the map phi, which takes k to k modular m, k modular n, is a bijection. And second, it preserves the addition. So preserves. So we want to derive our claim from this one. So we want to show that this map is a bijection and it preserves multiplication. So first of all, let me show that psi is a bijection, is a well-defined bijection. So what does it mean that it's well-defined? Well, if we take an element from here, it goes here. We already know that there is one-to-one correspondence between these two sets. But if we take an element from here, well, it may happen, like in general, that its image is not here, but just here in this product. So the well-defined means that if we take an element from here, it goes inside this subset of this one. This is why I use the well-defined word here. Okay, so, oops. So suppose we're given a number here, which what does it mean that k is inside this this subset? It means that k and m times n are coprime, which means they do not share any common prime factor. But it should be clear that this is equivalent to another condition, that k doesn't share any prime factor with m and doesn't share any prime factor with n, which means that k and m are coprime, and k and n are coprime. But this means that k modular m belongs to Zn star, and this means that k modular n belongs to Zn star. And here we see that k is in this set if and only if modular m is here and modular n is here, which means that, oh, I'm sorry, modular m is here and modular n is here. So which means that this bijection induces this one. So under this map, all numbers coprime with m times n goes to pairs of numbers from here. So this proved the first part of the claim that the map psi is a bijection. So from that, it follows that psi is a bijection. And now we only need to show that psi preserves the multiplication. And then by definition, psi becomes an isomorphism of groups. But in order to show that it preserves the multiplication, we just need to compute. So take two numbers from here, and we need to compare psi k1 times k2 and psi k1 times psi k2. And we want to check if these are the same. And this will be the second part for being isomorphism between groups. But now, by definition, the left-hand side is this. So you times n, and then you send it to a pair k1 times k2 modular m times n, k1 times k2 modular, wrong thing here, just modular m, and the second element in the pair is modular n. So this is the left-hand side. So this guy is equal to this one by definition. And when we compute the right-hand side, so first we compute psi of k1, which is k1 modular m, k1 modular n, then multiply it by psi of k2, which is k2 modular m, k2 modular n. But now, by the definition of this operation, we must multiply these two elements and put the result in the first coordinate, and then multiply these two elements and put the result in the second coordinate. And we will see that this is exactly what's written here. So if the right-hand side is this, so then we see, just by definition of this operation, that these are the same. So this completes the proof. Let me show you the whole proof again. So first of all, the claim, we claim that the same map as in the original Chinese remainder theorem is an isomorphism, but between these versions of the groups. We apply star here, and the map is still an isomorphism, but the operation here is multiplication. And the first part shows that the map psi is a bijection, and the second part shows that the map psi preserves the operation. And that's why psi is an isomorphism of groups. If you have any questions, please ask. If not, then let me show you this result. Well, now if we want to compute, say, Zm star, or let me say Zn star, where n has this decomposition into powers of primes, then this group is naturally isomorphic to a group this to the power ps to the power of ks star. So now, if we want to compute Zn star for any arbitrary natural number, it's enough to compute the same group, but for a power of prime. So now I want to explain you how to compute this group for a power of prime. And I want to formulate the result, but I'm not going to prove it because we're not ready to prove such a result. So the claim, so suppose pi is an odd prime. Then the answer is this. So the group Zp to the k star is cyclic. That is, it's isomorphic to this. So it's a cyclic group containing p to the k minus 1 times p minus 1 elements. That's the first part. And so this simply means that there is a generator. So this group is generated by some remainder a that is for any natural number from 0 to this number excluded, goes to the element a to the power n, and every element here is uniquely represented in this form for each element n from here. So the second question is how to find such an element a, and here is the answer. So a is a generator for the group ZPK star, this is k, if and only if two conditions holds. Two conditions hold. Well, the first one is a must be a generator, is a generator for Z.
Sorry, is it isomorphic or homomorphic?
Could you repeat your question, please?
Is it isomorphic or homomorphic, the sign here?
The sign here means isomorphic.
Okay, thanks.
And the arrow below shows how the isomorphism works from right to left. So it's easier to write this isomorphism from right to left, and it's almost impossible to write the inverse map from left to right. And we will utilize this property later on today when we will describe cryptography. So, but now is the boring part, but believe me, this is the last boring result today, and immediately right after I formulate this claim, we will do some cool stuff. But now we have to suffer a bit. So again, where we are. I'm trying to explain the conditions on a remainder A in order to be a generator for this group. So first of all, we take its modular P, and it must be a generator for this group. Well, this is a painful condition because you have to check it by brute force, but you have to check it once because here P is a prime number. We don't have to deal with an arbitrary K. And the second condition is the following. We raise 8 to the power of pi minus 1, and it must be not equal to 1 modular P square. So the condition on the left depends on K, and the condition on the right doesn't depend on K, which means that if we choose an element A satisfying these two conditions, then it will be a generator for every K for that group. So this covers the case of any odd prime number. Now we need to cover the second, the other half of the claim, which is the case of even prime numbers. And as you know, there is a department of even prime numbers on mechanical mathematical department. So in Moscow State University, so there is a whole department studying even prime numbers. So suppose now P is an even prime number, which is 2. And the answer here is a bit more interesting. So if I take Z2 to the K star, then there are 3 options. K is not greater than 1, K is 2, and K is not less than 3. In this case, the group is isomorphic to 0. So it's a group with 1 element. In the second case, the group is isomorphic to Z2, the cyclic group with 2 elements. And in the later case, we have Z2 times Z2 to the K minus 2. So it's not cyclic. In this particular case, the third option gives you a non-cyclic group. And so now the second question is how to produce these isomorphisms explicitly. So if K is equal, if K is 0 or 1, well, it's just a trivial group, so we don't have to provide any kind of isomorphism. It just consists of 1 element. If K is 2, then, well, Z4 star is isomorphic to Z2, and, well, there are 2 invertible elements here, 1 and minus 1, which is, yep.
Why when K is 2, we have Z2?
Okay.
It shouldn't be like Z4.
No.
Because 2 to the power 2 is 4.
When K is 2, here we have Z4 star. Okay?
Ah, yeah, sure. Yeah.
Yeah, and in Z4 star means that we take all coprime with all coprime numbers with 4.
Yeah,
and
but isn't 3
only,
prime with 4?
Yeah, 1 and 3.
But they are not included in Z2.
But no, these
isomorphic, sorry, yeah,
not an equality, it's an isomorphism.
Yeah.
So we have a map, and the map is this. The element 1 corresponds to 0, and the element minus 1, which is 3, corresponds to 1 here. So so the generator here, the generator A here is minus 1 or 3. These are the same elements. Okay?
Yeah, okay, thanks.
No problem. And if K is this, then Z2 to the K star is isomorphic to Z2 times Z2 to the K minus 2. And an explicit map, an explicit rule is given from right to left. So if we have two reminders, a modular 2 and b modular this number, then they go to -1 to the a, 5 to the b. So -1 is the generator for this factor, and 5 is element from this group is uniquely presented in this form, where a is 1 or 0 and b is any number from 0 to 2 to the k minus 2 minus 1. So these are all possible cases. So in case of an odd prime number, this group is cyclic, and in case of a power of 2, we have these three options, and here are the explicit maps from the right to left. Well, technically, this allows us to compute any group Zn star for any natural number n. We will practice during the seminar session how to do this. But for now, let's abandon this result and switch to a more interesting thing, which is cryptography.
But we won't prove it now, yeah?
What again?
We will not prove it now or today.
No, we're not going to prove this. It's not going to happen. Like, we will die. Like
Yeah.
you and me together.
Let's prove it.
So yeah, but what's more important is to learn how to use the result. And we will spend some time during seminar session for that. Because it's important to know how to prove the result, but it's even more important to know how to use the result. Because, well, you know, it's funny, but mathematicians, well, when they start learning something, they usually know how to prove everything. But when you ask them, well, let's apply this, even inside math, let's apply this result to prove something, they can't do that because no one teach them how to use the results. Everyone just teach them how to prove the results. And yeah, this is really funny. So we're going to stick to the second option, how to use the result. Okay, now cryptography. So let me describe the setting. There is you, your spouse, and your lover. And you want to send a secret message to your lover and discuss the details of your private meeting. But it's dangerous. Why? Because recently you have found a receipt from a gun store that someone in your family bought a shotgun, and you're 100% sure it wasn't you. So it's dangerous, but you want to send a message. Not sending a message is not an option. Remember, that's very important. Private meeting. So what to do? Cryptography to the rescue. We need to encrypt our message in such a way that our lover would be able to decrypt it. And we cannot meet each other. So we, like, for example, you live in Moscow and your lover lives in New York. So you cannot just go by feet and tell her or him any secret information. So there must be a way to do it remotely. So how do people do this? Well, there is one general idea. So when you do something in math, well, some operations may be very easy to do in one way, and they are very hard to do in the opposite way. So it's very easy to compute something in a direct order, and it's very hard to compute it in reverse order. And we may utilize this to encrypt and decrypt the information. So in order to encrypt the information, we apply our operation in a direct order where it's very easy to compute. And in order to decrypt the operation, our message, we have to apply the inverse map, but it's hard to compute, so no one can decrypt it for free. But if you know some secret information, then this operation becomes cheap. So that's the main idea. So we have to find these beautiful maps that are very easy to compute in one way and very hard to compute in the other way. And I'll show you an example. So there are several examples. The first one, so let me show examples of the operations. First of all, so suppose you're given two integers. Well, it's very easy to compute their product. Like everyone can do this. But now, suppose that you're given an integer and you want to factor it. So you want to find all prime factors. This is a hard to compute operation. So it's very easy to multiply and very hard to factor a number. And there are methods using these pair of maps. This, which is RSA actually. I'm not going to discuss RSA algorithm. The second thing, which is called discrete logarithm problem. So for the second problem, we take some group G, just a group. We take an element G from this group. Then, we, for any say, natural number n, we can easily compute the power of the element G. And there is a fast way of computing a power in any group. It's called exponentiation by squaring, a fast way to compute a power. So you can do it in log n steps, actually. So, and the map in the opposite way is this. So you're given an element H in the group G, and you want to find an element n such that G to the n is equal to H. So this is the map in the opposite direction, how to find the required number n. Well, the situation here is this. If you take an arbitrary group G and an arbitrary element G small, then both operations may be easy to compute. But if you take the group G and the element are very carefully, then the first operation is easy to compute, but the second one is hard to compute. Let me demonstrate you these options.
Is it like additional group and we can multiply two big prime numbers, something like this?
What again?
I think no, it shouldn't work now, nothing.
Okay, well, so let me show you two examples, probably even three examples. So example number one, if you take G to be Z and G small to be 1, then, well, what does it mean that you want to raise an element G to the power n? Well, here the operation is addition, so raising to a power means multiplication. So if you take an arbitrary natural number, then it's really easy to compute this thing. You just do it like immediately. And what does it mean to find the inverse map? So now h is just an arbitrary integer, and you want to find an element n such that n times 1 equals k. Well, it's obvious that we should take n to be k. So in this case, both maps are easy to compute. Like,
what if we choose like n and g to be two big primes? Would it help?
but then g is not a generator. I mean, in this
group, yeah.
If g and n are two big primes, then g and h are two big primes, then h is never over a power of an element of the element g. So I mean, in this case, there is no such n that the nth power of g is h. So the second, so this is an example of a bad choice. A second example of a bad choice is Zn. In this case, you take g to be 1, and well, again, raising to power is just multiplication. So, let me say zk. I want to n to be reserved for raising to a power. So for any natural number n, the raising to a power is just multiplying by n. And if you are given an element h from zk, oops, I'm using too many letters for denoting different stuff. So if we are given an element h which is a remainder a modular k, then the logarithm problem is this. You want to solve this equation modular k, which is trivial again. You just take n equal to n to be a. Well, here you can switch a generator. You may take like any integer which is co-prime with k. So you may say, let's take g to be some number m, such that m and k are co-prime. But then this problem becomes n times m is equal to a modular k, and you're searching for this guy, and m and a are known. But this also is not a hard problem. You can find an inverse element for m with respect to multiplication using Euclidean algorithm. I'm not going to discuss this here, but this is also a very fast operation. So it's not a hard one. So this is also a bad choice of a group. And a good option here is this. You take g to be zp star, where p is a prime number. And you want it to be a very, very large prime number. G here is just some generator for this group. It's a generator. Well, it's unpleasant, but you have to find a generator here. You do it by brute force. There are some tricks and hacks how to speed up the computation of a generator for this group, but I don't want to discuss them here and now. But you just choose any generator. Then raising to a power, so if n is an arbitrary natural, then raising to a power is computed like this. And there is a fast algorithm for raising to a power for any number modular p. I'll show you such an algorithm for any group. And the second, the inverse operation is this. So if you're given an element h from zp star, which is in case of prime every non-zero remainder, and you want to solve the equation g to the n equals h modular p, and you're looking for this guy. So here, this is the right choice. So this is the hard problem. This is hard. So if p is a very, very huge prime number, then this is a hard problem. The hard problem means that the only way to solve it is just a brute force. You just have to go through all elements, through all possible powers, and check them just one by one. So as you may guess, if p is a huge number, then this group contains p minus 1 elements. So if like p contains like 100 digits, it never happens that you find such a number by brute force. So this is a good option. Oh, this was an option number 3 actually, not 2. So this is a good option, and this is not the only option. There are other cases. Let me just name the cases. In general, there is such an object in algebra which is called field, and if you take a finite field, we'll discuss them later. If we take a finite field, we can take its multiplicative group. It doesn't matter that you don't understand the words now, but I just want to pronounce all those words for you now. So there is some similar object like ZP star, but produced in a more complicated way, such that multiplication here is even harder. But rising to power is still a very cheap operation. By this problem, discrete logarithm problem, is much harder for this group. And other option is the option of an elliptic curve. We're not going to discuss this, but I want you to know the words. This object came from an algebraic geometry, one of the hardest parts of mathematics. So elliptic curve over a finite field. So they are very, very effective. I mean, the rising to power is very cheap here, but this problem is one of the hardest ones. So this is a state-of-the-art option in general. So if you really want to know cryptography, you should learn all this stuff. And this is your #1 option. Okay, so that was some general stuff. If you have any questions regarding this, please ask. If not, let me switch to the cryptography itself. By the way, do you know the exponentiation by squaring algorithm?
No.
Again?
No.
Nope.
Okay, so let me show you. So fast way of rising to a power. So suppose you have a group G, an element G small, and a natural number n, and you want to compute G to the n. And you want to do it, and you want to apply these many operations, like logarithm n operations. How would you do that? So let me demonstrate the algorithm for a particular case when n is a power of 2. And actually, I want to demonstrate it in case n to be 8. And 8 here is 2 to the power of 3. So I'll show you how to compute the 8th power of each element in 3 steps. So we want to compute G to the 8. So what we do first, we present this as this. And now we apply our first operation. We compute this guy, just rising element G to the square. And this is our new G. G1 is G to the square. So this is our first computation. Now this becomes G1 to the 4, which is G1 square. And now we apply our second operation, which is raising G1 to the second power, and we will get G2, which is G1 square. And this will be G2 to the power of 2. And here we apply our third operation, and we will get the result.
Ah, you meant fast power raising algorithm?
Yep.
Yeah, we were familiar with it.
Oh, okay. Then it's good. And just in case, just for the sake of completeness, if we have like an arbitrary number n, which is not a power of 2, say n is 5, then what would you do? So in this case, you just need to present 5 in this form. It's a sum of powers of 2 with coefficients 0 or 1. And then it allows you to write down an expression like this. So this is how you compute an arbitrary power for an arbitrary integer n. But since you already know the algorithm, that's good. Actually, the algorithm will be written in the lecture notes, so I think we can skip it now and switch to the main part. So Diffie-Hellman public key exchange. Diffie-Hellman approach. Okay, let me say it like that, Diffie-Hellman. So let me describe the general situation, what's going on here. So first of all, when you want to send a message, usually so there is an original message. Original message is usually a string containing letters, or say, for example, in English alphabet. So, but you have some, so it belongs to some initial set S, usually just a set of strings, like strings. Then, we're not going to deal with strings. Instead, we want to deal with elements of a group. So we need to, at the beginning of the whole process, we fix a group G, which is cyclic. And we fix its generator G small. So G is a generator. And we want to denote the order of the group G n to be n. So we have these three pieces of information. A group G, an element, a generator of the cyclic group G, and small is the amount of elements in our group. So we will fix all these things, and they are well known to everyone. So everyone knows these three pieces. So everyone can use them while broadcasting or while trying to encrypt or decrypt the messages, even those who are not supposed to take part in the conversation. So our spouse definitely knows all these things. So first of all, when we want, okay, so first, if we have a string, we cut our string into pieces of a fixed length, like D. Then we map every element to an element of a group And this is done via some table, some lookup table. For example, we say that, okay, so we list all the strings, and we say that this string goes to this element, this string goes to this element, this string goes to this element, and this table is well known to everyone. So we have a table. Here we have our strings, and here we have the elements of the group G. So here strings, and here elements of the group G, H1, H2, H3, and so on. And using this table, we can transfer string messages to the elements of the group and go in the opposite direction. For an element of a group, we can find the corresponding string. And this information is also well known to everyone. So everyone can use this information. So this is not a part of our encryption. But the important impact here is that instead of dealing with strings, we will deal with sequences of the group G capital. Then there is some interesting step which is called encryption. I will explain it later. So what is an encryption in general? So on the higher level. So encryption means that we transform each element of a group to a different element of a group. So we transform each element of the group to something different, which is, say, M1, then M2, and M3. And then we send these new elements to our lover. And then he or she must perform a decryption in order to recover the original elements H1, H2, H3, and then apply our lookup table in order to get the original strings we were supposed to send. So this is a high-level picture for any encryption algorithm. So we start with our string, we cut it into pieces. For each piece, we have a table mapping our strings over fixed length to elements of the group G. Then we apply our encryption, send these guys to other participant. Then the other participant must decrypt the information and then apply this table in the opposite direction in order to recover the original string. This is how it works in general. And now I'm going to discuss this part only. So I'm not going to discuss these parts because, well, it's just a simple operation. The interesting part is going on here. So for us, the message is just a sequence of elements of the group G. And I want to show you how to encrypt and decrypt elements of the group. If there are any questions now, please ask. If not, then I'll proceed with explanation how to encrypt and decrypt the messages. Okay, so actually, I was in a rush writing Diffie-Hellman. So what actually I should have written it here, because now I want to explain you the Diffie-Hellman approach. So let me recall the situation. So we have three participants: you, your spouse, I'm sorry, your spouse, and your lover. So first of all, we fix a group G, an element its generator G, small, and compute the order of the group. And this information is known to everyone. So we have group G, its generator G, and element N, which is the number of the elements of the group G. So we broadcast this information and it becomes available to everyone. So everyone knows these elements. It's not a secret. Now we have to choose, before starting any communication, you and your lover must produce a secret key, which is an element of the group G. But how would you do that? So let me describe the first step, is how to produce the secret key. And then will be the second step, is how to encrypt and decrypt the information using the secret key. First, you choose a reminder modular N. And you do not tell this information to anyone. So the red color means this is a private information. Only you knows this information. Nobody else knows this. So your lover do the same thing. Chooses some reminder modular N. Again, no one, even you, no one knows this secret number. Then you compute the element of the group G, which is G to the power of A. Let me write it like this: G to the power of A. And similarly, here you compute an element S, which is G to the power of B. And then you broadcast this element to everyone, and your lover broadcasts his own element S. These guys are called public keys. So the blue color denotes the public key. So this is the public key. Public means everyone knows these keys. So let me clarify one thing. Everyone knows the element R, which is an element of the group G, but no one knows the element A, because finding the element A using R, G, and all the other information means that you have to solve the discrete logarithm problem for the elements G and R. And this is hard if the group G and the generator G small were chosen carefully. So even though everyone knows these information, no one knows these and these. But now, after this step, you see the public key of your lover, and your lover sees the your public key. So now both you and your lover knows the public keys. So let me write it here, and I want to put the straight lines to separate the information. So now both, just in case, here must be a comma. Now you want to compute the secret key. And how would you do that? You raise the public key of your lover to the power of A. And if you see what was S was G to the B, so rising S to the A, you compute G to the AB. And your lover does the same thing, computing rising R to power B, which means that as the result, we will get G to the power AB. And now, this is the end of the first step. Here, you and your lover both have the secret key, which is K. And no one knows this secret key. So this is the first step. Before starting any communication, you do this first step in order to produce this secret key. This is how it works. So are there any questions how it works? Should I repeat the process? Should I overview the process again? Okay. So this was step number 1. Let me even write it here. Now the step number 2. Communication. So you want to send a message. And now we have all these information here. So how would you send a message? So now, what is a message? So you have a private message. A private message is an element of the group G. So you want to encrypt the message. Encryption means that you multiply your message by the public key. So this is an encrypted message M. Now you broadcast this encrypted message and becomes available to everyone, even to your spouse, and your lover gets the message. And now, if you want to decrypt the message, how would you do that? You just multiply it by the inverse of the key. So the secret message becomes available via this computation. Just multiply M by the inverse element of the secret key. But how do you compute the inverse element of the secret key? So you use the Lagrange Theorem, which says that if you raise every element to the power of here to the power of n, you will get the identity element. So the inverse element can be computed via this formula, k to the power n minus 1. So rising to a power is a fast operation, multiplication is a fast operation, and this is how you restore the original message.
Could you say one more time, please? Where do we take n minus 1 from?
Oh, okay. Let me clarify this. So we have the group G, and we know that its order is n. The Lagrange theorem said that if you take an arbitrary element from this group, I take the name H on purpose because I don't want it to be confused with G, because here it doesn't matter whether H is a generator or not. But for any element of the group G, H to the power of the amount of elements in the group G, which is H to the n, is 1, the neutral element of the group. This is one of the corollaries of the Lagrange theorem. But now you see that H times H to the power n minus 1 is equal to 1, which means that this element satisfies the definition of the inverse element. And since the inverse element is unique, this guy must be the inverse element of H.
Okay, now it's clear, thank you.
Okay, no problem. So this is the whole process of communication. So you take your secret message, you multiply it by an element, by the private key, then you transfer this, and then you decrypt it by multiplying, well, actually by dividing it by the private key. And just in case, since the group G was cyclic, because it has the generator G, then the group is commutative. So the order of the operands doesn't matter. I mean, I'm writing H times K, or here M times K inverse. Well, it doesn't matter the order of the operands. So I could write it here like K times H, and the same formula here. It doesn't matter, but just in case. So everything here is commutative. So we're living in a finite abelian group, which is even cyclic. Okay, this is the whole magic. Now, let's try to understand, well, why this is safe, why it's impossible to decipher this guy. Well, actually, in order to decipher the message M, we need to find the private key. And in order to find, well, this is not a proof, but this is just an idea where the proof comes from. So in order to find this secret message, we need to find this private key. But in order to find the private key, what kind of, so we have to solve this discrete logarithmic problem, actually, because what do we know? We know element G, we know G to the A, and we know G to the B. And in order to compute G to the AB, we need to recover either A or B. Well, I have to prove this, and there are some approaches how to prove, well, rigorously that, well, this is actually a robust way of sending messages. Well, this is a safe way of sending messages, that the algorithm is robust. Well, all these techniques are beyond our abilities, so I'm not going to prove it strictly, but I want you to feel the reason why this is actually a good method of for communications. Okay, are there any questions regarding the process of communication? Okay, but here is a stupid question. How do you send the answer to this request?
Excuse me, and I've got a question. How do we encrypt the messages? So you said that we're dividing our message into strings D, and
yep.
then we associated them with the elements of G. But what is this association?
Oh, it's any chosen association. So let me show you an example.
I have to deal. I have to. I don't know how to say. To
let me show you an example.
My partner.
Well, so for example, suppose your strings are so example. Suppose all your strings are just strings of ones and zeros. Okay. Like message, it's something like this. Okay. And now I take a group Z5 star, for example, which is isomorphic to Z4. Each element here is just a power of 2, so K goes to 2 to the K. This gives you a unique representation of each element here as a power of 2. So this is your group G. And your generator is 2. Okay? And here is 4. Now, how many strings of order of length 2 you have here? You have 4 strings. Yeah. So let's just write a table which sends this guy to 1, this guy to 2, this guy to 3, and this guy to 4. These are all elements of the group Z5 star. And these are all possible strings of length 2. And this gives you a bijection. So this gives you the table that mentioned in the process of encryption.
Yeah, but it is known by both your partner and yourself and your spouse.
Yeah.
You know?
Yeah, everyone knows the table. So you actually transfer this, you broadcast this table. Everyone knows. It's a part of protocol. So usually how people do this, they write something like RFC with some long number where they describe a protocol. And inside this protocol, they predefine a group G, which is usually determined by some large prime number. They describe, explicitly describe the generator, and they explicitly describe some table for translating your strings to the elements of the group. What we really want, so this is not a secret to anyone. It's a well-known thing. And the important part here, you want, well, here it's a bijection between all the strings of length 2 and all the elements of the group. But in general, it's hard to find a number here and a bijection here. But so usually you want, so what you really want, so you want an injective map from left to right. For example, if you take all strings of length d, you have 2 to the d elements, and you want your group G to have at least 2 to the d elements. So you want this inequality, and then it gives you an injective map. You just produce some injective map from here to here, and you want the images of the sequences to be uniformly distributed inside the group G. So you don't want to put them at one specific place. You just want randomly put them inside the group G. This provides you with a good table. So you want this to be almost a bijection. So you want to take as many, so you want to cover as many elements from your group G as possible. Okay. So that's the main process. So if you, so now again, if you want to encrypt a message, you multiply it by a private key. If you want to decrypt it, you divide it by a private key. And if you want to send a response, you just encrypt it by the same way. You multiply it by a private key here, send it to another participant, and it decrypts it by multiplying it by k to the -1. Now, let me discuss several ways to make it even better. So how to make the process even better? You actually may change a private key each time you send a message. So let me show you how to do this. You suppose and you'll have. So here we have G small n, G small n, G small n. Well, now suppose that your lover is very talkative, and you want to listen. You don't want to interrupt her or him. It could be dangerous too. Who knows? So in this case, you may do the following trick. You choose a reminder A and produce your public key, which is again this thing. And you tell this public key to everyone, including your spouse. Oops. And now, if you want to, so now we're going to send messages from the right to left. And we do this. For each step, we produce a new number bk from this group. For each number bk, we produce our own secret secret key, public key, which is G to the bk. So k is a number of steps, and we have h1, h2, etc. hm, probably m is not a good choice. ht is the sequence of elements which represent our message we want to send. So we we compute. So here, since we know this public key R, and we produce this this thing, we can encrypt our message in the following way. So we have a public, a private key, key K, well, which is not a very good name, but okay, let's stick to this name. Using this formula, you raise the public key to the power bk, and this is your private key on the k step, which becomes a to the bk. And now you encrypt the first message using the first private key, the second message using the second private key, the third message using the third private key. But in order to decrypt this message, you have to know the public key sk itself. So you send pairs like this. So you send S1, which is your first public key, and you send, let me write it like M1, where M1 is H1 times K1, and you broadcast the message. Then you produce S2 and M2, where M2 is H2 times K2, where K2 is your second private message, and you broadcast this. So let me show you the whole process again. So what's going on here? So your lover knows your public key, and when he or she wants to transfer a secret message, for each step, he or she produces a new private key using your public key and her or his own element bk from Zn, and produce this thing, and then transfer this pair to you. So at the end of the process, you and your spouse will know all these pairs as one. Let me go to the. So at the end of the process, everyone will know all the pairs. And now we want to decrypt the messages. How would you decrypt them? So, so let me demonstrate the decryption process for the first pair. So we know that S1 is what? It's just, oops, it's G to the power B1. And we know that M1 is H1 times K1, which is G to the A B1. And we want to extract this H1 from the message. We use exactly the same procedure as we used before. So for that, we need to find the secret key on the first step. So the first secret key, which is G to the AB1. So the first secret key we find rising S1 to the power A, which we know. And the result will be G to the power AB1. So we know how to compute this. And then, in order to get H1, we'll multiply M1 by K1 inverse, and we compute it using all the information we know here. So K1 to the power n minus 1. But now the difference is this. For each step, we have our personal, well, we have a specific public key and a specific private key. And this makes this communication process even more robust, even better. I'm not sure that it was clear enough what's going on here, so let me show you the whole process. If you have any questions, please ask now. So, okay, well, to be honest, this is probably the first time when I completed the lecture quicker than I expected. So we have 4 minutes, and this is all I wanted to present today. So if you have any questions, please ask. If you want me to explain something or to repeat something or to make some overview, just don't hesitate to ask again.
To make this a two-way conversation, should you like store your old public keys?
Oh, well, you mean the second?
Yeah, the second way.
Well, you want to store your own public key, but when the communication goes, the public key on each step is sent together with the encrypted message. So you don't need to store this. After decryption, well, you don't need the public key as one.
I mean, when it's like two ways, like you send to your lover and your lover to you, your public key also changes.
Oh, then it works like this. Well, sending this public key, I'm saying now I want to listen to you and use this public key to tell me something. Then your lover sends all these messages, and then he or she sends you a new public key saying that now I'm going to listen to you and use this new public key to communicate with me. So then you store this new public key, like S prime, for example, and then you forget your own public key and you produce the messages in the opposite way, generating new public keys for each step.
Okay, I see.
So this is like a request, I'm ready to listen to you. This is how it works.
And lookup tables are basically Unicode? Or something like that?
Yeah, this is a part of the protocol.
Yeah,
So
okay.
you just fix it at the beginning. So because encryption happens here, not here. It's just a way to translate one alphabet to another one. So you may think of elements of the group G like an alphabet. And this is a well-known way of translating this alphabet to this one. Well, one additional thing here. Usually, let me go back here. If you take D to be 1, it means that you translate each symbol of your initial alphabet to an element of the group G. That's a bad idea, because it means that you encrypt each symbol. It's not a good way. So usually you want to take a larger piece of your string. So you want to translate like a lot of sequences at the same time. So, well, there are 2 reasons why you want to do that. Usually your group G is large, and your English alphabet is small. It's like 26 symbols and plus like space, comma, period, like exclamation mark, etc. But it's like 30 elements or like 30 elements plus. And these guys like hundreds of million elements. And you want this table to be almost bijective. It must be injective and almost surjective. Almost means like, well, a very small amount of elements of the group do not appear on the right-hand side of the table. So that's why you want these strings to be of a sufficiently large length. Okay. Are there any questions? Well, if not, then thank you. That's all I wanted to say. Thanks for being here, and see you next time.
Thank you. Bye.